Hello. We will learn about the London depth and coherence length for this lecture. From the outline of the basic theory of superconductivity, we will cover the coherence length from the Meissner effect section and the penetration depth from the London equation section. First, here is the conceptual question for the penetration depth before we head into the content. The question is, how do we explain the Meissner effect by penetration depth at the boundary between the normal conductor and superconductor region? Second, the superconductor consists of normal electrons and superelectrons. Normal electrons have a lower degree of order, and superelectrons have a higher degree of order. Finally, we come to the coherence length, which is related to the density of superelectrons. Penetration depth can be explained by discussing its phenomenon and its theoretical understanding. First, the Meissner effect refers to when a specimen transitions into a superconducting state, causing the internal magnetic field that was penetrating it to be pushed outward, resulting in the internal magnetic field becoming zero. At this point, the magnetic field can only penetrate to approximately lambda, known as the penetration depth. Any magnetic field penetrating deeper than this depth rapidly decays to zero. Due to this characteristic, the penetration depth can be used to explain an essential property of superconductivity, the Meissner effect, demonstrating that the magnetic field decreases gradually rather than instantly becoming zero. Second, an attempt to mathematically understand the Meissner effect using Maxwell's equations led to physical inconsistencies due to the B=0 phenomenon of the Meissner effect. By artificially adjusting the equations, it was possible to theoretically explain the phenomenon of the Meissner effect using the concept of penetration depth. This implies that the Meissner effect is an intrinsic property of superconductors. Note that the London equation is an assumption, not a fundamental theory explaining superconductivity. It is merely adopted to provide a physical explanation for the Meissner effect. Next is the coherence length. First, the coherence length is a spatial parameter describing the distance over which the superconducting and normal state transition occurs. The density of superelectrons increases with the coherence length. Similar to the penetration depth, the density of superelectrons cannot instantaneously increase, and the transition from a normal to a superconducting state cannot occur abruptly but changes gradually over the coherence length. Second, inside a superconductor, as magnetic fields penetrate deeper beyond the penetration depth, there is a sharp decrease in the density of normal electrons and an increase in the density of superelectrons, indicating a region where this phenomenon occurs known as the order parameter delta. The coherence length is a combined result of the penetration depth and the order parameter. Also, the coherence length decreases if impurities are present in the superconductor. For this lecture, we have covered the penetration depth and coherence length. First, penetration depth refers to the distance a magnetic field can penetrate until it becomes exponential of -1 of the surface magnetic field, beyond which the magnetic field rapidly decays to zero. Second, coherence length is a spatial parameter describing the distance over which the transition from a superconducting to a normal state occurs. The density of superelectrons increases with the coherence length. Third, penetration depth explains the Meissner effect occurring at the boundary between a normal conductor and a superconductor. Finally, the magnetic field and the density of superelectrons do not change instantaneously but gradually over the distance through the superconductor and the coherence length.